Hello there, it's Alana Tucky, and I'm back for more lecture videos. This time we're going to cover section 1.5. Before we get into that, I just want to do a little preamble, which is it's one for my notes, page 185 in the Winter 2014 course pack. Who knows what it'll be for future. Just a little refresher reminder of some definitions. So a statistic is a descriptive measure of a sample. So now that we've been so far in the course, you can think about that as like the sample mean. Right? When you have a sample, you have a mean for that sample. A parameter is a descriptive measure of a population. So if you knew the whole population, which happens when you have probability distributions, let's say for chapter 6, then that's a parameter. So in chapter 6, we would talk about the mu and the sigma, whereas in chapter 3, we were talking about x bar and s because we were working with samples. Now, inferential statistics is what the whole back half of this course is about. It's when you take samples and you extend to a population. So you say, hey, this little sample worked like this, so I'm going to guess that the whole population is going to work like this. And we try to measure the reliability of that result. Now, there's something called sampling error, which we talked about way back in chapter 1, which would have been chapter 3 a long time ago. Namely that's an error that comes from sampling. Because you're using a sample, it is never going to be perfect, right? Your sample statistic is never going to be exactly your parameter. It's just not going to happen because you're working with a sample which is automatically not the whole population. So it's not going to work like the whole population would work, right? But as long as it's random and unbiased, your sample is random and unbiased, then your sampling error should be relatively small. Now notice I'm using a lot of language like should and hopefully, right? Because having a truly unbiased sample that's representative of your population and is large enough, that's a little tricky thing to do. And we'll talk about how large they need to be later on in chapter 9. But suffice to say, you will always, always, always have sampling error. It always is there. It's always going to exist because you're using a sample, which is a subset, to guess about a population. So the population's all the individuals you look at. The sample is the subset of that. You usually get to know values of samples, right? You can know the sample mean. You can know what proportion of them think that, I don't know, M&Ms are the best candy bar or whatever. Well, M&Ms aren't technically a candy bar, but you get my point. And it depends on samples. So every sample is going to be slightly different. The population values is some constant. What percentage of people think Snickers is awesome? Well, you don't know what it is. You could sample people and get a sample of that what people think it's awesome, and then you can use that to guess about the population, right? But you don't know for sure. All right, so let me give you an example. Suppose we are interested in estimating the population mean price for pumpkins across all 50 states. So you want a population value. You want to know the average for all 50 states. Okay, so shown here is the mean 2008 price per state for pumpkins from a sample of 5 states, right here, 5 states, in cents per pound as published by the U.S. Department of Agriculture. So what's the sample? Well, the sample is the 5 states, right? Indiana, Michigan, New York, Ohio, PA, I think is for Pennsylvania. Now the population is all 50 states. Now find the sample mean price per pound. Well, we learned how to do that way back in the day. So stat, edit, let me clear this out. Enter this data, 15, 16, 36. And then we'll go to stat, calc, one variable. I don't have a frequency list this time, so I'm going to clear that out. So I just want L1, no frequencies. The only time we use the frequency list is 3.3 and 6.1. 3.3, which is when you have weighted means for group data, and 6.1 when you have expected value means with the probability distribution. So you can see that it is 21.4. So let me type that in. There we go. 21.4 cents per pound. Oops. I'm just going to put CTS for cents. I'm not sure where the symbol. Let me see if I can find the symbol. Well, I can't find it, so we're just going to have to live without. Okay, so we have 21.4 cents per pound. Now, what is the parameter of interest? Well, it's the population value. So the parameter of interest is the average price per pound for pumpkins in all the states. oops, all the states, right? We don't know what its value is, so we don't know the value, but we think it should be close to 21.4 cents per pound. Okay? Now, we don't know the whole thing because we're working with a sample, right? We don't know all of it, but we think it should be close. Now, what problems might there be with this sample? So if you look at this sample, think about where these states are located geographically. There are all the states, so these are only Midwest / industrial states, right? And it's possible that we took this with a random sample, but even so, having a sample like that, it's a biased sample then. Here, look this way. So it's a biased sample. Whether the parameter is even close to, that means whether the parameter is close to 21.4 like we think, is suspect. Is under suspicion, let me put it this way. Under suspicion. It's possible, but not likely with a sample this biased. Okay, so now let's move to section 1.5. Actually, let's not. Let's pause here and I will start the next video at 1.5. All right, see you then.